We talked previously about an intuition of approaching when we look at the graph of the function f of x equal 1 of x here. So we see that we take values that are close to 0, then the image of those values go up to values larger and larger, right? So we have value that is approach, value in the outputs that is approached when a value in the inputs is approached as well. We say that the limit of the function f of x when x tends to c is L if whenever I fix some values around L, I would be able to find corresponding values near to c such that f of x will be close to those values here. The quantity L might not even be a finite number, might be plus infinity or minus infinity, or it may not be defined. And it has another property that it might not be the same, depends on how I approach C. And this is actually what will happen with the function 1 over x. So we introduce also sometimes the notion of left limit. So when I add a little minus here, so this is called the left limit. And it means that I'm approaching C but from values on the left, so that is from the negative side. If I want to consider the right limit, so that is approaching values from the positive side of x, so above x, then that is called the right limit. That's the right limit. Left limit and right limit may exist, may not exist, may exist both of them but be different. But if they exist and coincide, then we say that the function is continuous. So let's look again at the function 1 over x. When I approach 0, then the corresponding values go all the way up, bigger and bigger. They don't stop actually, because as we know, the vertical axis is an asymptote, so that means that 1 over x will not close here. And similarly with the values from approaching 0 from the other side, from the negative side, go to the negative part of the y-axis. So for the reciprocal function, we have that the following limits exist, but they do not coincide. So we have that lim of when x tends to 0 minus, so this side, this is minus infinity, because I can go all the way down, and the lim when x tends to 0 from the positive side is plus infinity. Yeah? So in the case of the reciprocal function, which appears in many contexts, we see that the function has different limits when x tends to 0, depends how it is approaching 0. If from the positive side, then it's plus infinity. If from the negative side, then it's minus infinity. Sometimes this would happen. When it doesn't happen, which also doesn't happen for a lot of functions, most functions that we will use will have a different behavior, and that is that both limits will coincide, the limit on the left and the limit on the right. And in that case, we say that the function is continuous at the point C. So we have the following definition. A function f is continuous at a point C if the left limit, lim of f of x when x tends to c by the left, equals the right limit, lim of f of x when x tends to c from the right, and that is equal to the value of f evaluated at the point C. Our third concept of today is the derivative. The derivative of f at C is given by the following limit. It's the limit when h tends to 0 of f of c plus h minus f of c divided by h. Let's look at what this exactly means. Let's look at the following situation. Imagine we have the graph of a function f of x, and we have the values c and c plus h here. So f of c is this, f of c plus h is this, and if I want to have, as sometimes we want in many applications, if I want to know how fast is the function f moving around the point C, I can do the following. I can consider the line joining these 2 points here, f of c and f of c plus h. So this is f of c and f of c plus h. So the sort of speed, as it is sometimes introduced, of the function at c will be equal to the slope of this line, so the inclination. So intuitively, the function grows faster if this line is more steep, and it grows slower if the line is a little bit more flat here. So this approximation, this quantity here, the slope gives me an approximation of the speed. So that is that f of c plus h minus f of c divided by c plus h minus c. That gives me an approximation of the rate of change or the speed of the function around the point C. Yeah. So this quantity, when we take the limit when h tends to 0, so that means we take approximations closer and closer to C. That's what's called the derivative. The derivative has a motivation that comes from physics, from studying variations of small quantities on physical phenomena, but it also has implication in other branches of modern life. For example, in business, the derivative has the meaning of marginal cost, marginal profit, marginal return, etc., that will be important in microeconomics. Just to give you an idea, so the marginal cost means the extra cost of producing one extra unit of a certain good. If you sell tomatoes, the extra cost of selling one more tomato is not very high. If you sell custom luxury bag, for example, or a luxury pair of shoes, then there is a higher marginal cost than that of selling one extra tomato. We will not calculate the derivative on our course through limits. We will use different rules to calculate it and to be able to easily get the derivative without relying on its original definition. But it's important that we understand where it does come from, so that we have this intuition whenever we would need it.